Welcome to Advanced Quantum Chemistry and my fourth and final lecture on correlated wave function methods. In this lecture, I want to talk about coupled cluster theory. The coupled cluster wave function looks quite different than all the wave functions we have seen so far. It is obtained by letting this exponential operator acting on the Hartree-Fock wave function. This means that in order to get the coupled cluster wave function, we first have to do a Hartree-Fock calculation to get orbitals, and with these orbitals we can then form the Hartree-Fock-Slater determinants and of course also other determinants. This operator T here in the exponential is called the cluster operator, and it has several contributions. The T1 operator here is called a single excitation operator because if you let it act on the Hartree-Fock-Slater determinant, it will generate all single excited determinants, multiplied each one with its own expansion coefficients. In coupled cluster theory, you can see that one calls the expansion coefficients actually not coefficients, but one calls them for historical reasons amplitudes. And correspondingly, one does not use C as the symbol for the coefficient or amplitude, but one uses a small t. Now the next operator in the coupled cluster operator, the T2 operator, that generates, acting on Hartree-Fock, generates all double excited determinants, each multiplied with its amplitude. And T3 then generates triple excited determinants and so forth. And for a system with n electrons, the total cluster operator therefore has contributions up to Tn, to an Tn operator, which then generates n-tuple excited determinants. So that's the cluster operator, but the question is now, how does this cluster operator work when I have it as the exponent for Euler's number? So how do I evaluate the exponential of a cluster operator? Well, I do that in the same way as I would do that if it would be e to the power of x. I just write up the power series expansion of the exponential function, and that is 1 plus x plus 1/2 x squared, or in general 1 over I factorial times t to the I. So expanding the exponential, I get 1 plus the t operator plus 1/2 t squared plus 1/6 t to the third power, and so forth until infinity. So here I've written it out, so that's 1, then I get t, and I inserted the expansion of t in the different excitation operators, t1, t2, t3, and so forth. 1/2 t squared with a different contribution, 1/6 t to the third, and so forth. Now in the next line, I have rearranged all these operators, now not sort of according to what the power was in the expansion of the exponential, but according, I group all the terms together which have the same excitation level. So 1, that's no excitation. Then I get single excitations. Well, I get single excitations from the T1 operator. In the next one, I have double excitations, and I get double excitations from the T2 operator, but I also can get double excitation here from 1/2 T1 squared. So T1 squared and single excitation, afterwards another single excitation, of course, gives also a double excitation. In the next parenthesis, I have grouped together all the t's which give us triple excitation. Of course, I have T3, then I have 1/6 T1 2/3, and then T2 T1, and so forth. Now, the double excitations which the T2 operator generates, that, remember, T2 acting on Hartree-Fock gives us all double excited determinants, and they all multiplied each with its amplitude, TIA, IJ, AB. These are so-called connected double excitations because it's multiplied with one combined amplitude for this double excitation. The T1 squared term, on the other hand, I've written it out here, which I get first let one T1 operator act on Hartree-Fock, which gives me a single excited determinant, for example IA, and then I let a second T1 operator act on it, which gives me then, for example, JB. So I get again a double excited determinant, but now the coefficient, the amplitudes are single excitation amplitudes multiplied together, and not one combined double excitation amplitude. Therefore, this contribution to the doubles is called the disconnected double excitations. Now, why do I have here two products of single amplitudes and a minus sign? Well, that comes from the fact that, of course, this IJAB double excited determinant I can generate in two ways. I can either first replace I by A and then J by B, which gives me this product of amplitudes, but I also could generate it by first replacing I by B and then J by A, which gives me this product of amplitudes. But in this way of writing that double excited determinant, of course, I have ordered in the way that A comes before B. And here I would have it in A and B interchanged. Now, if I do that permutation, that gives me the sign change. So that's where the minus sign comes from, by putting the orbitals in double excited determinant, which goes with this product of amplitudes in the same order as that goes with that, and that gives a minus sign. I can also write it here. I sum freely over A and B and I and J, which I don't do here in this expression for the connected double excitations. And if I want to combine those two in one summation, then I also can restrict the summation 1 here. And then I would have to multiply the amplitudes by 2. So this takes 1/2 away. Now, these disconnected double excitations are clearly not the same as the connected double excitation. Well, the determinants are obviously the same, but the amplitudes by which the determinants are multiplied, meaning the expansion coefficients, are different. Now, I said before that this coupled cluster wave function is quite different than, for example, a CI wave function, configuration interaction wave function. Well, let's have a look whether this is react on here. So I get 1 acting 1 times Hartree-Fock, then I have a T1 operator acting on Hartree-Fock, and then I have this T2 plus 1/2 T1 squared acting on Hartree-Fock. Let's look at this expansion once again. Because if I only would include the T1 operator in my cluster operator, so it only would consist of single excitations, then of course here I have 1. T1 will generate me all single excited determinants. 1/2 T1 squared will generate all double excited determinants, but of course only with the disconnected amplitudes. T1 to the 3rd power will generate all triple excited determinants, but again only the disconnected one. And in the next one I will get a T1 to the 4th power, which will give me quadruple excited determinants, multiplied again only with the disconnected amplitudes. And that means that already when I only include T1, or whenever I include T1, I actually will get, because of the expansion of the exponential, I will get all excited determinants in my wave function. However, the expansion coefficients for anything higher than the single excitation will be in all cases only this kind of disconnected amplitudes. However, as I said, the coupled cluster wave function is the case. Now I have inserted my cluster operator, the expansion of the cluster operator, in my coupled cluster wave function and let it force. And that's what I've written up here. So I get Hartree-Fock, I get all sum over all single excited determinants multiplied with the amplitudes, a sum over all double excited determinants multiplied with the connected amplitudes, and here the disconnected amplitudes. Now our CI wave function looks like this. Again, also I have Hartree-Fock plus single excited determinants multiplied with the CI coefficient plus double excited determinants and so forth. And you can clearly see that I have absolutely the same determinants included in both the coupled cluster and the CI wave function. The difference is in the amplitudes. Here, because for the double excitation and all higher ordered excitations, I will have connected and disconnected contributions. And then secondly, as we'll see a bit later, the way how the coefficients or amplitudes are determined are different. In configuration interaction, we use the variation principle. In a couple cluster theory, we use something else, which we'll see in one of the next slides. So, I have these disconnected terms in the couple cluster wave function. And you might ask yourself, what are they doing? And they're actually very important. Because it's because of these disconnected terms, the couple cluster wave function or the couple cluster energy is size extensive. Now remember, in the case of the configuration interaction wave function, I talked about the example of having two hydrogen molecules so far apart that they do not interact, and then calculate the energy of this non-interacting dimer with the configuration interaction single doubles wave function, and compare it with the energy calculated with the also couple configuration interaction single doubles wave function of the monomer. And obviously the energy of the dimer, if the dimer is not interacting, should be exactly twice the energy of the monomer. But if one does this calculation with the configuration interaction single doubles wave function, this is not the case. Which means that the configuration interaction single doubles wave function does not scale correctly with the size of the system. One says it is not size extensive. But a couple cluster wave function, because of these disconnected terms, is always going to be size extensive, which is quite an important property and a big disadvantage of couple cluster wave functions. So the difference between configuration interaction and a couple cluster wave function, if they include determinants of the same excitation level, is actually not in the determinants, but it's in the coefficients or amplitudes. Now, if we include in the cluster operator cluster excitation operators up to the number of electrons, then we will get all determinants, all excited determinants which are possible in the given basis set, which mean that the couple cluster wave function has the ability to be as the full CI wave function, to be the exact wave function, the exact solution to the Schrödinger equation in the given basis set, of course. But this is really necessary to include excitation operators up to Tn in order to get all excited determinants. It has the possibility, can include all excited determinants, so it has the possibility to be equal to the full CI wave function to the exact solution. So I can easily insert it in the Schrödinger equation, which I've done here, and some people call this now the couple cluster Schrödinger equation. The next question is now, how do we get the energy? How do we calculate the energy in couple cluster theory, which is then how do we get the couple cluster energy? Well, of course, we could, like in configuration interaction, we could calculate as an expectation value, where we would have in the bra, again, the couple cluster wave function. But now it's important to remember what I've just said, that as soon as we have the T1 operator included, the expansion of the couple cluster wave function will give us all determinants. Which means in this expression, we have on both sides all determinants included, which means calculating the energy for whatever couple cluster model we use, couple cluster singles, couple cluster single doubles, and so forth, will actually have as many terms as the full CI wave function. Because of the exponential, we get all determinants included. Which means this is very, very expensive to calculate. So one could calculate the couple cluster energy in this way, but it's not a very good idea. So what do we do? Well, instead of doing it like in configuration interaction, we do it like in perturbation theory. Remember, in perturbation theory, in order to get expressions for the energy, one would use the different order equations, zeroth order, first order, second order equation, and then project it against the zeroth order wave function, which means multiply from the left and integrate with the zeroth order wave function. And we do precisely the same here. We project our couple cluster Schrödinger equation against the Hartree-Fock determinant, which in a way is the corresponding to the zeroth order wave function in perturbation theory. So if we do that, here on both sides of the Schrödinger equation, on the left and the right hand side, this is still absolutely exact. Then on the left hand side we get this integral with Hartree-Fock, the full Hamiltonian and the coupled cluster wave function. And on the right hand side, well, the energy of course is a number, so I can take it out of the integral. We get an overlap integral between Hartree-Fock and our coupled cluster wave function. If you now insert the expansion of the coupled cluster wave function again, we get the first term is Hartree-Fock with Hartree-Fock, and the Hartree-Fock wave function is normalized, so this gives a 1. The next term, if we take the expansion where I group the terms together according to their excitation level, so the next term is T1 acting on Hartree-Fock. That gives me a single excited, that gives me all single excited determinants. But which means that these determinants are different than those determinants, and this is just an overlap integral. And remember, for the Slater-Condon rules, the overlap between the two determinants is only different from 0 if they are exactly the same. But this is Hartree-Fock, and this is a single excited, so this is 0, and the same happens for all other terms in the expansion of the coupled cluster wave function. So on the right hand side now we have just standing, this is just 1. Which means by doing that we actually get an expression for our coupled cluster energy. The coupled cluster energy is equal to this integral Hartree-Fock, Hamiltonian, and the coupled cluster wave function. Now let's look at what kind of terms come out of this integral. So I've written up here again. And I now insert my expansion of the coupled cluster wave function again. And remember, the first term is Hartree-Fock. So we get Hartree-Fock, Hamiltonian, Hartree-Fock. That's just the expectation value of the Hamiltonian with the Hartree-Fock wave function. And that is our definition of, or the definition of our Hartree-Fock energy. The next one again is T1 acting on Hartree-Fock. That gives all single excited determinants. But please remember from my lectures on Hartree-Fock theory that the matrix element of the Hamiltonian with Hartree-Fock and a single excited determinant, that is 0 because it's equal to the element of the Fock matrix with an occupied orbital and a virtual orbital. And if the orbitals are the eigenfunction of the Fock operator, of course this part of the Fock matrix is 0. The next term then are all double excited determinants, the connected and the disconnected one. So this is a double excited determinant multiplied with some amplitudes, but still a double excited determinant. And according to Slater-Condon rules, this is of course not 0. The next one is then triple excitation. So I have the connected triples and the two different ways of disconnected triples. So this gives me then triple excited determinants multiplied with some amplitudes. But Slater-Condon rules say that if I have Hartree-Fock, Hamiltonian, and triple excited determinants, these are all 0 because there's a difference in more than 2 orbitals between the two determinants, and that correspondingly applies to all the higher terms. Which means the only thing which survives here are actually only the double excited determinants. And there's no approximation, nothing in that. That's just a consequence of that we have projected against Hartree-Fock and the expansion of the coupled cluster wave function, and of course the Slater-Condon rules. So the coupled cluster energy is the Hartree-Fock energy, and then one correction to this, one extra term, which consists of this matrix elements of Hartree-Fock, Hamiltonian, and double excited determinant, and multiplied with these connected and disconnected amplitudes. Now that matrix element we already have seen. That's the same as we have in the Müller-Blechett second order energy correction. Slater-Condon rule says Hartree-Fock, double excited, that's a difference in 2. So we get one pair of Coulomb minus exchange integrals. Which means we actually have the same integrals as we had in the second order correction in Müller-Blechett perturbation theory. The difference, of course, is in Müller-Blechett perturbation theory, we had one fixed expression for the coefficient. That was actually just these integrals again divided by the orbital energy differences, where here we have now our connected and disconnected coupled cluster amplitudes. And on the next slide, we have to figure out how to get those. But before I do that, I just want to stress once again that the expression for the coupled cluster energy, which is this one here, is the same for all different coupled cluster methods. So it is the same independent of what kind of excitation operators I include in the coupled cluster operator. The only thing I have to include, of course, is the T2 operator. If I don't include the T2 operator, I would not get this term. Or if I don't include the T1 operator, I would not get this term. But as long as I have a T1 and a 2 operator, I will get this full expression. But whether I have a T3 or T4, T5, whatever operator, they can't contribute to the energy because of the Slater-Connon rules. Okay, let's look at the amplitudes. How do I get the amplitudes? Well, again, like in perturbation theory, where in order to get the first and second order corrections to the wave functions, one takes the different perturbation theory equations and now projects them with one of the other zero order functions, not the ground state zeroth order function, but one of the other ones. And we'll do the same here. So now we project our coupled cluster Schrödinger equations not against the Hartree-Fock determinant, but against any of the excited determinants. And what I'm going to illustrate this here now for one particular coupled cluster method, meaning for coupled cluster doubles to make the expressions or the equations a bit more compact, shorter, which means the T operator now only consists of the T2 operator. Okay, so my original coupled cluster wave function is the Hamiltonian e to the T2 acting on Hartree-Fock, and then the coupled cluster energy and the same one. And I now project these coupled cluster Schrödinger equation against one double excited determinant, A, B, I, G, on both sides. And if I look at this now, let's look over here. This is again, it's just an overlap integral. It's the overlap between a double excited determinant and all the sum over all double excited determinants multiplied with their coefficients. And of course, the overlap between two determinants is 0 as long as it's not exactly the same determinant. So the only term which in this summation here of T2 which survives is the term which has the same double excited determinant, and they are orthonormal, so that gives me 1. So the only thing I get out is then the coefficient, the double excitation coefficient which belongs to this determinant. So I have on the right hand side I have the coupled cluster energy multiplied with this amplitude, which means that by projecting against the coupled cluster Schrödinger equation against this double excited determinants, I actually obtain an equation for the amplitude of this determinant. Now on the left hand side I have to expand here again my coupled cluster wave function. So I get, as the first one, I get 1, which means I get Hartree-Fock. Then I get T2 here. And then I will get 1/2 T2 squared, and so forth. I will get more terms. But all the higher terms are 0 again because of Slater-Connon rules. Because if I get more, if I get the next term would be 1/6 T2 to the third power. That gives me a hextuple excitation. So I would have a hextuple excitation here and a double excitation, and Slater-Connon rules say that this is 0. Whereas this one is just a quadruple excitation, and I certainly can get something out of a double excitation Hamiltonian and a quadruple excitation. So you can see the expansion also for the equations for the amplitudes, the expansion of the coupled cluster operator, the exponential operator here breaks off because of the Slater-Connon rules. Now, of course I have to do that with all possible double excited determinants to get equations for all their amplitudes. So I get as many equations as their double excited determinants, which I of course need because I have to find all the double excited determinants, double excited amplitudes. Now let's look at this second term here. That's a double excited determinant. I've written it up here, double excited determinant, Hamiltonian, and the sum over all double excited determinants written up like this. Now this is double with double, so I will, this is not zero, at least not in general zero, so there will definitely survive several of these matrix elements. Which means here on the left-hand side, I actually have a summation over terms which include the doubles amplitudes. In the equation, which is supposed to be the equation for one double amplitude. Which means the equation from which I want to determine this double amplitude IJAB, unfortunately, on the left-hand side, includes all the other ones. Which means I cannot solve this equation alone. I have to solve them iteratively. So I get a similar situation as we had with Hartree-Fock equations, where the elements in the Fock matrix actually depend on the molecular orbital coefficients, which are things which I want to get from the Hartree-Fock equations. So I have to do an iterative solution again, like Hartree-Fock or Kohn-Sham, where I have to guess, in the first time I have to guess what these amplitudes are here on the left-hand side of the equation. Then I can evaluate what the amplitude on the right-hand side is. I do that with all my equations, and I get a new set of amplitudes, which I have to stuff in here on the left side again, and evaluate what my new amplitudes are. And I have to do that until the amplitude don't change again, sort of self-consistency again, like in the Hartree-Fock equations. Which of course is much more complicated than in Müller-Plesser perturbation theory. So coupled cluster is an expensive method because one has to iteratively solve these equations. These equations here for the double amplitudes, where in the CC2 model one has made some approximations. And one of the approximations, for example, is that this term is neglected. Now, what are the most used coupled cluster models? Well, the standard sort of coupled cluster models is coupled cluster single doubles, where you include the single excitation operator and the double excitation operator. There is an approximation to this method. It's called CC2, which was developed several years ago in Aarhus. And the approximation is actually in the equation for the double amplitudes. So it is that's CC2. It actually performs quite well. What is called the golden standard of quantum chemistry, meaning the best method, quantum chemical method, which is still routinely used or can be routinely used in calculations, quantum chemical calculations, that is CCSD parenthesis T. That is essentially, in the first place, is coupled cluster single doubles. So one does a coupled cluster single doubles calculation as normally. But then one adds, so one gets the coupled cluster single doubles energy. But then one adds a correction to that, which includes triple excitations. But it's not correction from coupled cluster equations, but one actually takes Müller-Plesser perturbation theory expressions from fourth and fifth order of Müller-Plesser perturbation theory, which include the triple contributions to the energy. So coupled cluster single doubles parenthesis T, CCSD parenthesis T is a mixed method. It has a pure coupled cluster single doubles contribution, and then it has a contribution where one uses the equation from Müller-Plesser perturbation theory fourth and fifth order for the triples contribution to the energies.